Okay, so the topic of my talk is the paradox of the positive, which is a famous quote, and I'll explain what that means in a moment. But in the context of the problem, it's exploratory tools for visualizing the individuals in a multivariate longitudinal data, or in generally multivariate longitudinal data. Some of this work is joint with Nick Tierney and Tania Prvan and a few other people. But so here's an example of how I got started in this topic. This is there's a famous book on longitudinal data analysis by Singer and Willett. And I picked that book up and was looking at it in about 2003. And quite a lot of lovely, interesting case studies in there. And this one is one that caught my attention. This is wages on the vertical axis, log wages actually, and experience in the workforce, the length of time in the workforce on the horizontal axis. And their model fitting used education and race as covariates. And the final model that they described is summarized by this plot. And what you see is that the model suggests that there's a difference in that based on the categorical variables. But generally wages go up the longer that you're in the workforce is a suggestion, but your wages go up more if you are more educated. That's the very dotted line at the top. And if you're not Black, it's not, we'll talk about racial issues later, but I'm not entirely comfortable with this breakdown. But so the suggestion for the model is that your wages, you can expect your wages to change based on your demographics. So I thought, oh, this is interesting data. I'll take a look. And at the time, I was working with a software system called ggobi and developing software for that. And I poured that data into the full data into ggobi. And I want to show you some of the things that you can look at with this old system. So this is a video, 3-minute video.
This video clip demonstrates exploring longitudinal data. The wages data is used as the example.
So the full data is really a blob, very messy. And what I'm showing here is this random sets of individuals. The line's not plotted for the individual, just the dots. So each time it blinks, there's a new individual's records. But the same variables are plotted here. Experience is on the x-axis and log wage is on the vertical axis. Just skip through a little bit. It's quite varied from one individual to another. Now that's just randomly selecting individuals, but if I now select individuals on the basis of different criteria that have been measured, so on the x-axis on the left-hand side plot, the standard deviation is plotted, and on the vertical axis, the differences between consecutive time points. So that way you could pick out individuals that have a higher variance and individuals that maybe have bigger jumps based on these criteria in the left. You'll see that there are quite a lot of individuals where the wages change a lot over their time frame in the workforce. This is actually 12 years maximum in the workforce, from 0 to 12 years in the workforce. If we zoom through a little bit faster on this, there's another set of statistics on the left. On the horizontal axis, it's a linear model, and it's a slope of the linear model is what is plotted on the x-axis in the left plot, and the same vertical axis as before. So points on the right-hand side would be increasing slope, but there's also a lot of individuals with negative slope as well, which means there's a lot of individuals whose wage experience during that time in the workforce was actually negative. So that's pretty surprising. Well, for me at that time, I thought that was really surprising. I expected that you work longer, you'll get more wages, or it would increase. And I was just surprised that at least this cohort of people, there's quite a lot that have a decreasing wage pattern over time. It is adjusted for inflation, but it's decreasing over time. And there's a lot of individuals that have extremely volatile wage histories. So the interesting thing, well, this made me wonder whether the model itself is the best way to summarize this data. And my argument is that for this type of data, we need some better methods for summarizing the variation for individual to individual, because the individual to individual variation is much greater than the overall trend. And while the overall trend seems to be sort of what we hang on to and sort of common belief, our individual experiences are much different from that. And as statisticians, we need to be able to better communicate that and better talk to the individual as opposed to the overall population. And so I think this is a big difference between statistics for policy versus statistics for the public. And statistics for the public really need to speak to people, not the general averages. And so that's a purpose of the tools that we've been developing in this, that I'm showing in this talk. So the title for the talk comes from a famous speech by Frederick Douglass. And at the time so he was a slave in historically his background. But at the time, the United States was making very strong statements about American values of liberty, citizenship, and freedom, at the same time as enslaving people. And so this is quite true whenever we're talking about general patterns and trends. What might be good for one person may be completely terrible for another person. And that paradox of the positive is a quote that talks to that, and so want to be able to give the sense of a broader sense of the whole experiences rather than just that general trend. Okay, so just a note on race, which is really important, because we do this all the time in statistics. We plug race in as one of the patterns, and it is important from a various perspective in terms of ensuring that our general policies are not inadvertently really benefit all demographics, how you break it down. But the problem with a variable like race is it's not in itself. Melanie Wall has a lovely quote that she put on Twitter a few years ago, which is really important. First, if racism is a principal factor organizing social life, why not study racism rather than race? And second, why use an unscientific system of classification in scientific research, which is race is a very unscientific classification and a very problematic variable generally to look at. So I'm not going to focus on that in the analysis. The only reference is based on the case study in Singer and Willett, because I have a problem with that variable. So I'm going to talk about new tools for longitudinal data that help you explore the individuals. And these are in the R package called brolgar. I'll give you the link to that later on. All right, so the wages data has this type of data structure. It's what I would call a long tidy form of data. brolgar turns it into a data object that's called a Sybil object, which is built by Iro Wang, which specifically recognizes a time index and also a key index. So it's really a useful data structure in R for working with temporal context data. So the Sybil, this has 6,500 observations with 9 variables. This exclamation mark means that this is not regular time data, so there's no regular period in time. The key is an ID variable, so the ID column in here is the key index, and there's 888 unique IDs. So there's 888 individuals in the data from Singer and Willett. And in terms of other variables, XP is the length of time in the workforce, and it is a real number, so it's calculated relative to the date they initially entered the workforce as reported by them. So the experience is the time variable, and the log wages is the response variable of interest. And then there's some demographic variables or covariates. And there's also a continuous covariate, which is unemployment in the area when the data was collected. So if we plot the full data, and this is often what happens when you plot longitudinal data, it just looks like a big hairball, or in this case, I'm going to call it a blob of spaghetti. So I plot it using ggplot, where experience is on the x-axis and log wages on the vertical axis, using a group variable ID so that the lines get connected just from between an individual's measurements. So that's one of the first things that you hit with longitudinal data, is trying to peek inside that hairball. I like these GIFs. So if you try to eat the whole bowl of spaghetti like this, it's a terribly horrible thing to watch. This approach is a little more controlled. It's still horribly awful to watch. And this one here is where we're aiming to get to be able to handle the spaghetti a little bit more perfectly. Good to watch, maybe not so fun if you're eating spaghetti, but that's our goal, is to be able to organize longitudinal data in a slightly more, in a lot more systematic way in order to extract all sorts of different types of insights from it. So the first step really is to investigate what you've got in the data from a sort of a bookkeeping perspective. And I'm going to skip fairly quickly over this. I just want to point out some things. When you've got measurements like this, you are likely to have a different number of observations for each individual. And that's what I plotted here. So for this data, we do have a range of just a single observation for an individual up to 13 observations. So there's a couple of individuals where we've got 13 observations. But for the most part, most individuals, we've got between 5 and 10 observations. So that's the first thing that you need to think about, is maybe we can't work with all the individuals because we don't have enough data on all the individuals, and I might need to restrict my analysis to maybe only 2/3 of the individuals, or I might even need to go out and understand, is there a difference between the individuals where I've only got one measurement? Maybe they dropped out of the study for various reasons, that systematic reasons, and so if I only work with the more complete cases, I might have a problem with my results. They might not be representative of everybody that could be studied. Right, so but we could take that and filter on it. There's a few other types of bookkeeping things we might do. I could look at differences in time measurements, but those bookkeeping variables are really important in terms of measuring them and using them to improve the quality of the data that you then pass further downstream in the analysis. So we could filter on the number of observations for individuals. Another thing would, another one might be starting at the same time. I'll just skip over that one. And then the range of time that people are studied. So working with the bookkeeping and improving the quality of the data that you, or at least understanding the quality of the data that you're working with by those is an initial first step. The next thing in terms of penetrating that hairball of data is just to take small spoonfuls, like the eating of spaghetti, to take a few strands and digest those before moving on. So in the brolgar package, we have a lovely function called sample and keys. And so you can say, I want to take samples of size 10 individuals or 3 individuals or 20 individuals. And you can do that repeatedly. So sample, 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 sample. And so here's a sample of 10 individuals. And that's fairly interesting. They're fairly long profiles. And most of them seem to be sort of increasing there. There's one very short profile where it's decreasing a little. And there's one profile at the top that's a little flat, fairly long. So with 10 individuals, we can roughly see the patterns in those 10 individuals. So let's then pick another 10 individuals. So next 10 individuals, you can see there's a couple of short profiles, one starting only about 2.5 years into the measurement cycle. And you still see some profiles that are steadily increasing, but you see now a couple of profiles that are fairly varied in the wages experience. Another 10, and another 10. Oh, sorry, another 10. So that way, similar to what we were doing with GIGO, but we could work our way quickly through the 888 individuals and just get a sense for the variability from individual to individual. Another thing that we might do is only look at the longer traces. So only just filter on the individuals that have 7 or more measurements in the data set, and then still sample and keys. So just see the difference between short profiles and long profiles. So those are long profile individuals. And then there's short profile individuals as well. And so the main purpose here is just getting small chunks of the data in order to digest what's in there with the individuals. So there's a couple of additional functions that can be useful here related to this. So faceting, if I don't like to have all 10 individuals in one plot, I might, I can break that out into a number of plots, and I can organize how many individuals get shown in each as well. So here's an example of that. So I've now sampled a lot more individuals, but I've faceted them out to just put 3 individuals in a single plot, just to try to dig into the individual experience. Alrighty, so those are all fairly simple approaches. The next step would be to calculate special features of the longitudinal measurements of the profile. So simple calculations like fit a linear model, simple linear model, or even a robust linear model, and return the slope and the intercept from that model for each individual. So each individual, and calculate the variance or the standard deviation for each individual, calculate the jumps in measurements or the differences in time for each individual. And I'm calling these longnostics. Way back in the 70s, John Tukey introduced a term called cognostics for computer-generated diagnostics that can be used for various things. The most recent work on that, still in the 1990s, was something called scagnostics for scatterplot diagnostics. And scatterplot diagnostics have scagnostics as all sorts of things that you can calculate on scagnostics that are measuring stringiness or skinniness or convexity, trying to summarize the patterns in scatter plots. Well, here we're trying to summarize different patterns that we might find in a profile for an individual. So I'm calling these longnostics for longitudinal data diagnostics. All right, so let's calculate some of these. And so there's a few that you can calculate automatically in the brolgar package. Add key slope will be calculating a linear model for each individual and adding the slope as a variable in the data set. And then we can use that variable to select out cases again, to select out individuals. So here I'm selecting individuals where they have a slope from that linear model fit of bigger than 0.4. I can still sample individuals among those, but I think there's only a few individuals that have a slope as high as 0.4, and that's these ones. Some of them are nicely, steadily increasing. One of them, it's a little bit misleading to use slope for that one because it's quite a varied wage pattern, even though the overall slope is upwards. So those longnostics can be used again to extract out different types of patterns, and again, just pulling subsets of individuals, and we can do this many times. These are extracting individuals where they have a pretty large negative slope. So there's 3 individuals here, and although the slope is negative, maybe that's not a great indicator. It's also their experience is really quite varied, except for maybe that shorter one here. But that way we can at least extract the individuals that have not had a great experience in the workforce. All right. Again, that's not terribly difficult, and it can be, many people do that as part of their data analysis as well. Here's one that's a little bit of a variation from what we might see. At least I've not seen this done anywhere in the analysis that I've examined. So taking those longnostics and making summaries of those to try to get a sense of, across the entire data set, what are the patterns, what is the distribution of patterns that we see in different types of patterns. So a 5-number summary for a set of longitudinal data, and using that to extract who might be an average. Do you have a question? Okay, so I'll move on. So using that 5-number summary to get, so what would be the average individual based on slope patterns, or so it's particularly calculated on a particular longnostic. So trying to summarize the whole body of the data rather than just extracting the top or the bottom. So there's a function called keys near in the brolgar package that will help extract that. So the 5-number summary will pull off the person who's closest to the minimum, the person who's closest to the maximum, the person who's closest to the median, person that's closest to Q1 and to Q3. So let's take a look at an example. Actually, I've got a 3-number summary as well as a 5-number summary. So if I look at the 3-number summary, that's extracting the individual who's closest to the minimum, closest to the maximum, closest to the median. And it's using the slope longnostic in order to do that. So this light purple line is the individual that has the lowest slope of all individuals. The slightly darker purple, so the slightly darker purple is the individual that has the highest slope of all the individuals, in quite a steady increase, but both of those are fairly short profiles. And the individual who's closest to the median slope is this dark black one here, fairly, and that's quite flat. So the median slope is close to 0. We can make the 5-number summary. I'm going to spread that out into 5 different plots now. So the 5-number summary, what's different is the Q1 and Q3 is added into here. And Q3, I think, is quite a long profile. Yeah, so just a scale change on the x-axis here. That seemingly long profile was really only 4.5 years of experience. But the Q3 goes up to about 9 years of experience. So the scale on the x-axis here has changed from the previous plot, but they're the same min, same max, same median. Q1 and Q3 as different. So what do we learn from that? Q1, the first quartile, it's still pretty flat. The median is quite flat, still quite volatile, but we're only looking at the slope characteristic. Q3 does have an increase, and the max is really a big increase in slope. So what we learn is that most of the individuals on the low side is closer to a flat wage history than a decreasing slope history. So it's only in the first 25% of observations between the min and Q1 that may have a negative slope. We could pull out more quantiles on this if we want to get more complete sense of, and we can look at the slope, the lognostic just itself, the distribution of that. But it's interesting to be able to look at the individuals that match that criterion. So it's so this, in terms of increasing wage patterns, once you get to Q3, that is an increasing wage pattern. So really there are more individuals in the data set that have an increasing wage experience over their work life than the other way around. That's a good thing to learn. Alrighty, so one more aspect. So just summarizing that last part, we can use these lognostics then to generate individual-based 5-number summaries on different characteristics. That's useful. And then lastly, we always want to fit models to the data. And so if I fit a random effects model to this data, using the LME4 package. So LMER is the function that I'll use. So it's still a linear model. And I'm going to use education as a covariate. And the random effects is going to allow slope and intercept changes based on a subject. So we can fit the model, and now we can show the fitted models for each individual. It's still, so these are the fitted models now for the data here. And you can see it's still like a block of spaghetti, maybe uncooked spaghetti because it's all straight, but it's still hard to really digest because there's so many cases. We do see a lot of the lines are going up. So that tells us that for most individuals, there's an increasing pattern in wages. Good. But we can also see there's a few straight lines that are pointing downwards. So there are still some cases. So the model is detecting those ones as well. Now, it's also very useful to be able to see how the model fit matches the observed data for each individual. So break it back down to individual level. And now you need to pull off a sample of individuals again. So we still need to use that sample keys. I'm going to sample 12 individuals, and I'm going to show the fitted model and the observed data for those individuals. And you'll see for the most part, it's pretty good. So the line is the fitted model, the points of the observed values. For the most part, individuals, the model looks quite good. And then you've got some massive mismatches. And look at this one. This is the one that's haunted me for more than 20 years now. Well, not quite 20 years. That the model fit that seemed to do quite nicely does extremely poorly on something as really basically obvious as this one. There's that the observed data is a nice, very steady decline in wage value, and yet the fitted model misses that completely. This is a really important reason for looking at fitted versus observed for individuals when you're working with longitudinal data, particularly when you're working with a random effects model, because odd things do happen, and it's good to know when that occurs. All right, so we can also look at multivariate. I'm going to skip over that for time reasons, but we could look at multiple measured variables at each point and use some of the high dimensional techniques that I've worked on before. But so just in terms of what I've shown you so far, some of these techniques are used commonly, and you'll see examples of it in places like the New York Times. And so the New York Times had some pretty nice COVID displays. They had some pretty awful COVID displays as well, but this is one of their COVID displays. So it's broken down by individual states. So individuals are states here, and that's quite nice to see just how the COVID experience is on a state by state. And then they've used longnostics to extract the states where cases are increasing or cases are decreasing or about the same. So they've done that calculation of longnostics to extract different types of patterns among COVID cases in the US. Alrighty, so just to wrap up, what I hope you've heard today is that as statisticians, we need to do more research and have acceptance of research on methods that can help communicate the individual experience. When the variation in a data set is large, really summarizing the variation is an honest thing to do, rather than just report the overall model averages. And as statisticians, we need to address that individual experience so we can better engage with individuals in the public. So just post log, that wages data that I showed you is a bit stale. There is a refreshed version available now. That data is an openly available data. It's a lovely resource, and it's still, the data is still being collected, the National Longitudinal Survey of Youth. There's a new package, yowie, that has data up until 2018. And the process for collecting new data is documented in this paper. So as the next cohort gets released into that database, we could refresh the data readily again. The problem with the old data is that that process to collect it was really not transparent. And the full data has 12,500 individuals, but there's only 888 individuals shown in that data set, which means there's some massive cleaning that had happened to that old wages data. And it's really hard to track back to get which of those people were included in that study and not. To use the brolgar package, this is the link for the package, brolgar.nicktierney.com, NJ Tierney. And brolgar is a beautiful Australian bird, and it is an acronym here for Browse Over Longitudinal Data Graphically and Analytically in R. And that's all I'd like to say today. Thanks for listening.